Picture Earth floating in space with an invisible shield wrapped around it. That shield is the magnetosphere, a vast bubble created by Earth's magnetic field. Every second, the sun fires a stream of charged particles toward us. Most of the time, the magnetosphere bends that solar wind around the planet like water flowing around a rock. And during a solar storm, the shield gets hammered much harder. For decades, scientists thought something reassuring happened when those storms became extreme. The magnetosphere seemed to reach a limit. Push it harder and Earth's response would stop increasing so quickly. Almost like a shock absorber reaching a point where it could somehow prevent the worst solar storms from delivering all of their energy into the planet. But a new study suggests that this safety limit may never have existed. It may have been created by a statistical illusion. And if the researchers are right, an extreme solar superstorm could affect Earth up to about twice as strongly as some previous estimates suggested. To understand how something this important could hide inside the data for decades, we first have to travel away from Earth. About 1.5 million kilometers toward the Sun sits a special region called the L1 Lagrange point. Several spacecraft monitor the solar wind from around this region, including missions such as WIND, ACE, and DSCOVR. Think of them as weather stations sitting far upstream in a giant river of plasma. When a solar storm passes those spacecraft, they measure its speed, magnetic field, and other properties. Then the storm continues toward Earth. A little later, it hits the magnetosphere. Scientists compare what the spacecraft measured with what Earth did in response. For moderate solar activity, the relationship is surprisingly simple. Stronger solar wind produces stronger electrical currents and plasma motion around Earth. If you draw it on a graph, the line rises. But when researchers looked at the strongest solar wind events, something strange happened. The line started bending over. The solar wind kept getting stronger, but Earth's response seemed to level off. Scientists called this saturation. And saturation looked important. If the magnetosphere really had a physical upper limit, then there might be a natural cap on how much energy an extreme solar storm could inject into the near-Earth environment. Over the years, scientists proposed numerous mechanisms to explain why that might happen. Perhaps the geometry of Earth's magnetic field changes. Perhaps the solar wind is diverted differently. Perhaps currents in the system rearrange themselves. At least 10 different theoretical explanations were developed around this apparent saturation behavior. But researchers led by Nitin Savadas at NASA Goddard asked a more uncomfortable question. What if there was nothing physical to explain? What if the curve was bending because the measurements themselves were misleading us? The problem begins with that 1.5 million kilometer gap between the spacecraft and Earth. Imagine standing several kilometers upstream from a waterfall and measuring the river. You see a violent wave pass you. Then you predict exactly what that wave should look like when it reaches the waterfall. But the river changes on the way. The wave stretches. Other currents collide with it. Its timing shifts. Its shape changes. So the extreme value you measured upstream is not necessarily the exact extreme value that finally reaches the destination. Solar wind behaves in a similarly complicated way. Between L1 and Earth, the plasma can evolve. Shock fronts move, structures change. And even the estimated arrival time of a solar wind feature contains uncertainty. Now add one subtle statistical effect. Suppose a sensor reports an extraordinarily extreme value. There are two possibilities. The event really was that extreme, or the real event was slightly less extreme, and random measurement uncertainty pushed the reading upward. And because moderate events are far more common than extremely rare ones, that second possibility becomes increasingly important at the edges of the data. This is related to a phenomenon called regression to the mean. Extreme measurements tend to correspond to true values that are somewhat closer to typical values than the measurements themselves suggest. Here is a simple way to picture it. Imagine a target board. Most arrows land near the center. Only a few land near the outer edge. Now imagine every arrow's position is blurred slightly before you measure it. If you select only the arrows that appear farthest from the center, some truly belong there. But others only appear extreme because the blur pushed them outward. So when you later compare those apparently extreme arrows with another measurement, the second measurement looks less extreme. It appears as if the system resisted the strongest input, but nothing resisted anything. You selected unusually noisy measurements. The researchers argue that something similar happened with solar storms. The most extreme solar wind measurements at L1 had the largest uncertainties. When scientists paired those measurements with Earth's response, the response looked weaker than expected. That produced the illusion of saturation. So the team tried correcting for the measurement uncertainty. And the bend disappeared. Instead of flattening at high solar wind strengths, Earth's geomagnetic response continued roughly along the same rising relationship seen during moderate conditions. More inputs, more responses. No clear safety ceiling in the observed data. The researchers tested the idea using data from several spacecraft, including Wind, Themis, MMS, Double Star, and Cluster. They also compared different ways of measuring geomagnetic activity. After calibration, multiple indicators showed the same basic result. The apparent saturation weakened or disappeared. That leads to the disturbing part. If Earth's response does not saturate where scientists thought it did, then rare superstorms may be more dangerous than models based on that saturation assumed. The Nature paper estimates that at very strong solar wind conditions, around 25 millivolts per meter in the study's driving parameter, the geomagnetic response could be roughly twice as large as previously inferred. That does not mean Earth is about to be hit by a civilization-ending solar storm, and it does not mean the magnetosphere provides no protection. Without Earth's magnetic field, the solar wind would interact with our atmosphere very differently. The magnetosphere remains an enormously important planetary shield. The new result is narrower. It says there is currently no strong statistical evidence that the magnetosphere automatically caps its electrical response during the strongest storms we have measured. And that matters because modern civilization has quietly become extremely sensitive to space weather. Imagine a powerful eruption leaving the sun. A huge cloud of magnetized plasma crosses space. Hours or days later, it slams into Earth's magnetic environment. The magnetosphere compresses. Electrical currents intensify high above the planet. Auroras expand toward lower latitudes, but the same changing magnetic fields that produce spectacular lights can also induce electrical currents in long conductors on the ground. Power lines, pipelines, communication infrastructure, large electrical grids. Satellites above Earth can face radiation, charging, and navigation problems. Radio communication can be disrupted. GPS accuracy can degrade. And during a sufficiently extreme storm, power transformers could experience damaging currents. The classic example is the Carrington event of 1859. A massive solar eruption struck Earth and produced auroras visible unusually far from the poles. Telegraph systems experienced electrical disturbances, with some equipment producing sparks. But the world of 1859 contained no satellite navigation networks, no global internet infrastructure, and no enormous interconnected electrical grids. A modern event of similar or greater strength would encounter a very different planet. That is why engineers care about the upper end of the solar storm distribution. They do not only want to know what happens during ordinary storms. They need to know what happens during the event that may arrive once in centuries. And rare events are exactly where measurement uncertainty becomes most dangerous. That is also why this study reaches beyond space weather. The same statistical trap can appear anywhere scientists study extreme conditions. Climate scientists may ask how infrastructure responds to a once-in-a-thousand-year flood. Doctors may study how patients respond at extreme levels of pain or blood pressure. Engineers may test materials near failure. Machine learning systems may learn from datasets where the most unusual inputs are also the least certain. If uncertainty exists in the variable being used to predict an outcome, regression bias can create artificial thresholds where no physical threshold actually exists. In other words, sometimes nature does not stop responding. Our graph only makes it look that way. There is one important limitation. The researchers do not prove that magnetospheric saturation can never happen. At solar wind strengths beyond the range adequately represented by current observations, some new physical mechanism could still produce a limit. The paper is careful about this. Its conclusion is not, saturation is impossible. It is, the existing measurements do not provide statistical evidence that saturation has already occurred. That distinction matters, but it also changes the question scientists now need to ask. For years, the puzzle was, what physical mechanism stops Earth's response from increasing? Now the better question may be, how strong can Earth's response actually become before a real physical limit appears? Future spacecraft could help answer that by measuring the solar wind much closer to the magnetosphere, reducing the uncertainty introduced during the journey from L1. Better forecasting models could track how individual solar wind structures evolve on their way toward Earth. And grid operators may need to reconsider extreme event scenarios that assumed the magnetosphere would soften the strongest inputs. There is something strange about the entire discovery. No new spacecraft had to discover a hidden particle. No telescope had to photograph an unknown object. No mysterious force had to be added to physics. The surprise was hidden inside data scientists had already collected. For decades, the graph seemed to tell a comforting story. Push Earth's magnetic shield harder, and eventually its response begins to flatten. But after researchers accounted for uncertainty, the shield behaved differently. The curve kept rising, and sometimes the most important scientific discovery is not finding something new. It is realizing that something we thought we had already found was never really there.